So, today we are going to start looking at how we will solve MDPs, right. So, the first thing I am going to introduce you to this notion of what is called as stochastic dynamic programming. Right? So, it's called stochastic dynamic programming. So, some of you have come across dynamic programming already in the algorithm design, right. So, it's kind of like a divide and conquer methodology, and where you take into account the repeated substructure that is present in the problem in order to solve. So, first solve a smaller problem and use the solution to solve a larger problem, right. So, that's basically the idea behind dynamic programming, and you will see that as we go along that we are using some form of dynamic programming to solve this. We already seen it a little bit, right. So, we solve the one stage bandit problem, and then we use the solution of the one stage bandit problem to solve the two stage bandit problem, and so on and so forth. We already looked at that earlier and how we generalize the bandit solution to the MDPs, right. So, likewise we are going to look at a very formal structure for estimating the value functions in an MDP. So, we looked at two kinds of value functions. One was the value function associated with a policy pi, and the second was a value function that is associated with the optimal policy, right. So, there is the V pi or Q pi, the value functions, state and action value functions associated with the policy pi, right. So, we looked at already, right. So, V pi and Q pi, right. These are policies associated with a specific, these are value functions associated with a specific policy pi, right. And then we also saw V star and Q star, which are value functions associated with optimal behavior or the optimal value functions, right. And so, what we will look at is the first cut solution approach is to look at dynamic programming based algorithms for finding both V pi and V star or Q star, right. So, that is where we will start off, and then slowly we will relax our requirements, right, as we go to solving the MDP, right. So, just a side note here. So, the problem of going from a pi to V pi, right, is called the evaluation, right. It's called evaluation. I am taking policy pi and I am evaluating it and finding out what is the value function corresponding to the policy pi. And finding V star is sometimes called the control problem, right. So, the finding V pi is called the evaluation or the estimation problem. So, finding V star or Q star is called the control problem. So, we can use dynamic programming approaches for solving both evaluation and control, right. So, the classically when people have been talking about Markov decision processes, right. So, MDPs appear a lot in domains such as operations research, right, and in sequential decision making and those kinds of areas. MDPs appear a lot. They are used quite extensively there. In fact, reinforcement learning borrows all the notions from operations research and allied fields, right. So, there dynamic programming is the solution method of choice for MDPs, right. So, this is what people use extensively. More recently, what has happened is that reinforcement learning in turn has started influencing how people use dynamic programming for solving MDPs, and so I'll make allusions to it as we look at these topics in the later classes. We are not going to get into quite too much detail on that, right. So, there are a few things that we should know about dynamic programming methods. As you will see in a bit, they require the complete knowledge of the MDP, right. You need to know the states, you need to know the actions, you need to know the transition matrix, right, and you need to know the rewards. So, the transition matrix is what? So, you need to know, basically you need to know P of S prime R prime given S comma A, that you need to know, or you need to know P of S prime given S comma A and the expectation of R given S A S prime, right. So, these are things that you need to know. This is what we mean by saying complete knowledge of the system dynamics, right. And dynamic programming can get computationally very expensive. In particular, right, every iteration of the dynamic programming can be very computationally expensive, right. So, the compute load, the peak compute load can be fairly high, right. But the positive side, most of these dynamic programming approaches, right, under the right conditions, they are guaranteed to converge, right. So, this is a big plus. So, you know that if you run these long enough, they will eventually converge under the right conditions, right. So this guarantee is unfortunately not available for all kinds of reinforcement learning approaches. Even though they work well in practice, we still don't know if they will always work, or if there are conditions under which these algorithms might not work. It will come down the line, so let's not worry about it too much, right. But then there is also this thing which people call as the curse of dimensionality, right? And the curse of dimensionality is present in all approaches, right. It's more a question of how large the state space becomes, right. So earlier we looked at simple MDPs, right. We looked at this kind of grid world, right. So where you had an x coordinate and a y coordinate, and you are numbering the states in order. So if it's a 5 by 5 grid world, you will have states running from 1 to 25, right. You could also think of that as 2 dimensions. So one dimension having 5 values, another dimension having 5 values, so that overall you have 25. But suppose you have like 30 variables that are describing your system, right, not just the x, y dimension. I remember the robot example I was telling you about, right. There are multiple sonar readings, bump sensors, and motor values, and so on and so forth, right, torque values, joint angles, and all of these. So there are so many different factors that can contribute to defining the state space, right. Now, if you think about a transition matrix, right, in that large state space definition, so you'll soon find that the system specification becomes very, very large, right. And if you add just one more variable, even if it's like a Boolean variable, right, you kind of make the state space grow very large, right. So that is the problem, right. So this is what we call as curse of dimensionality. So the larger the number of dimensions that describe the space, the more exponentially does the size of the state space grows, and therefore it makes it prohibitively expensive even to write down the system dynamics in analytic form, so that you can use it for dynamic programming approaches. So that makes dynamic programming fairly hard to scale for very large problems. And methods that work without a complete specification of the system dynamics scale much better, and we say that they don't suffer from that much from curse of dimensionality. So that's essentially what we mean by curse of dimensionality here. And so that's actually sometimes mentioned as one of the drawbacks of using dynamic programming like approaches to solve MDP. So there are ways of getting around it, but fundamentally there is a problem that we have to think about. Okay. So let's look at the first example, right. So we're going to talk about policy evaluation here. We're going to talk about the policy evaluation step. So policy evaluation is, given a policy pi, right, we want to compute the state value function v pi. Given a policy pi, we want to compute the value function v pi. Okay. So how do we go about doing this? Recall that we have the Bellman equation for v pi, right. So what is the Bellman equation for v pi? So v pi of s is equal to the summation over a, summation over s prime and r. So the summation over a of pi as, a given s, and summation over s prime and r of p of s prime given r, s prime and r given s comma a times r plus gamma v pi s prime. Okay. So this is the Bellman equation for v pi. So we know that. We have seen this already. We know how to derive this and all that. So how are you going to solve for this Bellman equation? So what we mean by solving for this Bellman equation? So what are the unknowns here in this Bellman equation? Yeah, again, this is more of a recap. The unknowns here are the v pi's, right? So the v pi is unknown. So you have v pi of s on the left hand side of the equation, right? You have v pi of s on the left hand side of the equation, and you have v pi of s on the right hand side of the equation also, right? So what do we mean by that? So you have v pi appearing here, right? So this is an unknown, this is also the unknown, and the same s can appear here also. It's not like it will appear only on the left hand side, right? So now if you think of it, I'm going to have, let's say the size of my state is s, right? The size of my state space is denoted by that symbol, right? So that's the size of s, and I'll have that many variables, right? So I have 1 v pi of s for each s in capital S, right. So I have size of s number of variables. Let's, for convenience, let's say this is n, right. So I have n variables, and how many such equations I have? I'll have one equation for each v pi of s on the LHS, right. So I'll have n equations, right. I have n variables, I have n equations, and what kind of equations are these? These are all linear equations, right. Even though there are so many products that are happening here, at no point will you see a product of two of the unknowns, right. I am not going to see v pi of s1 times v pi of s2 or v pi of s1 squared anywhere, right. So these are all going to be linear equations. So that's basically what we are here. So v pi of s, again v pi of s on the right hand side. There are no higher order terms. So it's a set of linear equations, right. So there are n equations in n variables. So these are simultaneous linear equations, and you have lots of methods by which you can solve it, right, provided you have the right degrees of freedom, and therefore the solution is well defined. It turns out, because of the way we constructed this Bellman equation, right, as a way of representing how the value rollout happens, right, how the return is rolled out as you are executing a policy pi, and the fact that your gamma is a limiting factor, right. So gamma is between 0 and 1. So this put together actually ensures that not only does this system of linear equations have a solution, it also ensures that they have a unique solution. There's a single solution for it. So for each policy pi, right, there's only one solution that satisfies the Bellman equation. We talked about this earlier, and there are some videos that you can refer to that will be linked as part of the additional reading material. So these videos are not required material. So if you want to understand why there is a unique solution to this v pi, you can watch those videos, right. So you could solve these as like simultaneous linear equations, a system of simultaneous linear equations. But there's another interesting way of looking at this, right. So this is where the dynamic programming part comes in, and also this is an approach that we will use later when we are trying to compute the optimal policy also, not just the optimal value function, not just for v pi, right. You could solve this whole thing iteratively. So how do we do that, right? So let's take a look. How do we do that, right? So I'm going to start doing this iteratively. So what I'll do is I'll take v0, right? That's, so I'm given some policy pi. That pi is fixed, right? So I'll take v0. I'll define it uniformly to be 0 for all s, right? Yeah, I'll define this uniformly to be 0 for all s. Now I'll plug in vk to the right hand side and compute vk plus 1 on the left hand side. So it's going to go something like this, right? So there will be vk plus 1 of s is equal to summation over a pi of a given s summation over s prime comma r p of right. So this was a little complex to solve because I had unknowns on both the left hand side and the right hand side. Now what I have done, I have rewritten it so that on the right hand side I have k, right, on the left hand side I have k plus 1. So k plus 1 are the unknowns, so vk plus 1 are the unknowns, but on the right hand side I have everything that is known because I already computed vk. So how do I do that? I start off by defining v naught equal to 0, right, I start off by defining my v naught equal to 0, and then from there I am going to plug in my v naught on the right hand side. Now everything is known on the right hand side, right. If I plug in v naught on the right hand side, everything is known on the right hand side, right. Now what I will do is I will compute v1, right, and then what I will do, I will take v1, I will plug it on the right hand side and I will compute v2, then I will take v2, plug it on the right hand side, compute v3. I keep doing this until, so when I go from some very large vn to vn plus 1, or so vk to vk plus 1 for some very large k, there will be very little change, right. Vk will look very similar to vk plus 1. At that point I stop, right. There could be some very small, say 10 power minus 3 difference between vk and vk plus 1. At that point I can stop my iteration and declare that this is my v pi. Okay. So it's a little, you could think it's a little wasteful. Why am I doing this iterative process? I have a neat system of linear equations, I can just solve it. It turns out this iterative process gives us a lot more flexibility in how we will arrange the computation and allows us to come up with more efficient ways of approximately solving the problem. While policy evaluation will solve the problem accurately, but will end up taking a lot of compute every time we go through this, while this kind of iterative approach, right, might allow us to solve these things more efficiently and also act as a building block for finding the optimal value function, as we will see in a bit, right. So let's think about what is happening here for 1 minute, right. I start off with V naught equal to 0, all zeros, right. So what will happen here? I'll plug that in here. So for k equal to 1, right. So k equal to 0, right. Start with k equal to 0. So what will happen is I'll plug V naught equal to 0. So this whole part will go away. So I'll be just left with R, right. So I'll sum over S prime comma R, probability of S prime R given S comma A into R, right. Summation over A pi of A given S. So I'm summing over all S prime, right. So all possible values of S prime, right. So this is basically, and I'm multiplying by the same R, right. So this is essentially saying that, okay, summation over R of probability of R given S comma A, right, because I'm summing over all S prime, so that's going to go to 1, right. So and then sum over A pi of A given S, right. So this is basically what I'm computing. So what is this expression? This basically tells me, okay, I'm going to behave according to pi, right. I'm going to behave according to pi. I'll take one action starting from state S. So that's what this is, right. I take one action starting from state S. Look at what the reward I'm going to get, the expected reward I'm going to get, right. This is the expectation of the reward I'll get for taking one step. I don't care where I land up, right, because I'm just done. I'm just taking one step. Get it? So this is basically V1 of yes. I'm just taking one step and I'm looking at the expected reward when I'm taking actions according to my policy pi. Right? This is basically what it says is this is the one step expected reward for policy pi. Does that make sense? So V1 of S is essentially the expected reward I'm going to get for taking one step according to policy pi. I mean, extending this, you can think of V0 of S as the reward that you will get for taking no steps, basically no reward, right? So that's why it started off with 0. Now that you have solved this for one step, right, I'm going to plug that into the right hand side, right? So let us just, for lack of space, I'm going to erase this. I hope it's all fine with people. Now what I'm going to do is I'm going to look at what happens when k equal to, so this I computed for k equal to 0. What happens when k equal to 1, right? So this will be R plus gamma V1 of S prime. Okay. That's basically just plugging in k into this expression. So what does this mean? So I'm going to start from state S, take action according to policy pi. Right, start from status, take action according to policy pi, right. I'll go to some next state S prime, right? Then I look at the reward I get for going to the next state S prime plus gamma times V1 of S prime. So what is V1 of S prime? Is expected reward I'm going to get for taking one step from S prime, right. V1 of S prime is the expected reward I'm getting for taking one step from S prime, right. And R is the reward I'm going to get for taking one step from S. Basically what has happened is I'm taking R plus gamma times the reward for taking one more step from S prime. So starting from S, how many steps have I taken? 2 steps, right. So when I say V2 of S, right, it's basically the 2-step expected return from S with the policy being pi, because V1 of S prime is already assuming you are taking actions according to policy pi from S prime, and here we are making the assumption you are taking action according to policy pi from state S also. Right. So now I used my one step expected reward and use that to compute my two-step expected return. So after I don't worry about what happens after my second step. It's just I'm just stopping at the second step here, right? So that's basically the second iteration of my policy evaluation. Likewise, what happens when k equal to 3? I'm going to get my 3-step expected return, and if as k becomes larger and larger, I'm going to get my infinite expected return, basically the complete expected return starting from S and behaving according to policy pi. So this is the basic idea behind the dynamic programming way of doing policy evaluation, right? That's why it's called dynamic programming, because I first solve the 0-step problem, which is by assumption making it all 0, right? And then I solve the 1-step problem, right? And then I use the solution I got for the 1-step problem and solve the 2-step problem. Then I got the solution I got for the 2-step problem and solve the 3-step problem, and keep going, right? So this is essentially why it's called dynamic programming. Okay, great. So let's look at it from algorithm, right? So just write down algorithm. So input is a policy pi, that's a policy that has to be evaluated, and then we have some threshold parameter theta. I told you, right? Some 10 power minus 3 or something that we need to keep to stop it, right? So we have some small threshold theta that tells you when you have to stop, right? And then we initialize, right? Well, you can technically you can initialize it to anything. I mean, initializing 0 is just to tell you how the dynamic programming part works, right? But algorithmically, you can actually initialize it to anything. It is still guaranteed to converge to the right answer, right? So you could initialize it arbitrarily, or you could initialize V of S to 0, right, for all S, right? But one thing I have to be very careful. So the final state, if there is a final state in this whole process, right, if there is a final state beyond which you can't go anywhere, you have to hold it fixed at 0. Because it doesn't make sense to say that, okay, I have come to the end, right, there is no more action that I can take according to my policy pi, right, but I'm still getting rewards, right, I'm still, there is an expected future return. That doesn't make any sense, right? So you have to set your final value to 0. This is something that you have to remember. Some later on what happens is people kind of tend to forget this. As you learn more and more complicated stuff, you tend to forget the fact that the terminal reward or terminal value function has to be 0, right? So the last bit, right, you have to hold it to 0 all the time, right? Just be careful. Whenever your episode ends, right, the value function that you plug in has to be 0. You don't have to, think of a specific terminal state and use a value 0 for it. It could very well be that whenever your episode ends, right, instead of doing this, you just use R, right? So you do this if doesn't terminate, right? And you do this the reward for the next state, right? Or if S prime is the last state in the episode, right? So you don't you're updating yes, yeah. So S prime is the last state in the episode. Then you don't use V of S prime in your update. It should just be R, right? In fact, I recently when I was teaching my RL class in person, right? So I actually discovered that a lot of students were actually using a library that is out there that doesn't do this, and it turned out because of this they were getting wrong answers when they are doing the simulation. So you have to be careful about it, right? Even though the algorithm describes it like this, remember that if you come to the terminal state in the episode, right, if it's truly the terminal state, not because you stopped training, then you should use this as your just remember this, right, this as an aside. So now what we do, we start off by setting some parameter delta. I'll tell you what delta is in a minute. We set delta to 0, and then for each state yes, right, then we basically start doing this, right? So we take the old value of V of S, that's the last value in the previous iteration, right? So this is basically the kth value, right? So you take Vk and store it temporarily in this variable V, right? And then you use your update rule, right? So this is essentially the update rule that we saw earlier, right? So this is basically K and this is K plus 1, right? That's what we did, right? This is K and K plus 1. So after you have done that, you compute the difference between the old V, Vk, and this is the Vk plus 1, right? So you compute the difference between Vk and Vk plus 1, right? And see if it is larger than the largest difference you have seen so far. If this is larger, then replace delta with this. If it is not larger, then leave delta as it is, right? So basically use the max, right? Then keep going until your capital delta becomes smaller than your threshold that you had earlier, theta, right? The theta could, like I said, could be 10 power minus 3. So keep iterating until the maximum difference you see from k to k plus 1 is less than 10 power minus 3. So that's basically when you stop, right? So this is the stopping condition. Just keep iterating otherwise, right? And again, I'm not going to get into the proofs today, but you can watch it on the videos that this is guaranteed to converge to a solution, right? It's guaranteed to converge and stop at some point, because this equation that we have here is what is called as a contraction operator, right? I'm not going to get into the details of it. You can look it up if you're interested, right? So you can think of it as, so the reason we are doing this funky thing, right? So why we are putting a V here and then comparing the capital V with the small v and all that is because we are trying to do this in a slightly more efficient manner, right? If I had done this, right? If I had done it like what I talked about here, right? Have a Vk here and a Vk plus 1 here and so on and so forth, you would need 2 copies of V, right? We need the k copy and the k plus 1 copy. So for us to do that will be wasteful of memory, right? So doing this update, right? So this is called a synchronous. This is called synchronous update, right? So this is some this is in place updates. In place update means I'm not making 2 copies of Vk plus 1. I'm just changing the 1 copy itself, right? I'm just changing 1 copy of Vk to Vk plus 1. So this algorithm is a little efficient algorithm, but it also hides a small fact. Think about it. So I'll show an example. I'll show a numeric example and then come back and talk about this algorithm, right? So the numeric example is going back to the greedy policy that we had earlier. Right? Sorry, going back to the random policy that we saw earlier. So here is a grid world, right? And it has 2 absorbing states. These 2 corners are absorbing states for the grid world. So go into either one of them and then you stop, right? And then we are talking and you get a -1 reward for all transitions until you stop. Right? So the optimal way of solving this problem is to get to one of those corners as quickly as possible and not move from there, right? But then we are going to talk about a specific policy pi, right? So the specific policy pi here is a random policy. So what we mean by random policy? That you could go in any direction with equal probability. So this is basically what the random policy is, right? So there's a 1/4 probability of going up, 1/4 probability of going down, 1/4 probability of going left, 1/4 probability of going right in all the states, right? That's what a random policy is, right? So I start off with Vk being all zeros, like I was telling you earlier. So we start off with Vk being all zeros. And what is Vk1? Vk1 is the expected reward you're going to get for taking 1 step, right? Vk1 is expected reward you're going to get for taking 1 step, right? So what happens when you're taking 1 step? It doesn't matter, because 1 step you're going to stop, right? So for that 1 step you're going to get a reward of -1. So you're not going anywhere. So you just take 1 step and you stop and you're getting a reward of -1, right? So it doesn't matter which step you took, whether you went left, up, down or right, you're always going to get a reward of -1. So you're going to get -1 into 1/4, -1 into 1/4, -1 into 1/4, so on and so forth. And so the total is going to be a -1. So you can see that for that 1 step function, all the states you get a reward of -1, right? And remember, these 2 will stay 0 because they are terminal states. You don't move from there. So their reward will stay 0. Okay. So I hope it's clear why all of this is -1, right? You're taking 1 step. It is not that because you're getting a reward of -, it's actually a little bit more complex than that, right? So because why? let me write out what happens here, right? This is the easy case, so I can easily write out. So remember, I'm going to sum over all A, pi of A given S, right? It doesn't matter what S is, this is going to be always 1/4, right? And then I'm going to sum over all S prime and R, probability of S prime R given, and then R plus comma V of S prime. So V of S prime is gone, so it's 0, so I don't have to worry about it. Let's worry about the other one, right? So action, say north, right? So I'm going to take north, so which is like 0.25 probability, right? And what is the probability I'm going to end up anywhere? So just one step, right? So basically I'm here, I go north, I end up in the same state, right? I end up in the same state with probability 1, right? There's no question about it, and I get a reward of -1 with probability 1, right? And what about gamma V of S prime? So what about gamma V of S prime? We don't care about it. So this is basically summation over S prime, which is probability of the same state, right? Probability of S, comma R, which is -1. So -1, and that this combination has a probability of 1. Everything else has a probability of 0. So it's 0.25 into 1 times -1 plus, let's say go east, right? Yeah, go east. So go east from here. So again, that's a 0.25, right? Times the probability of going east will put me in this state. So that's the S prime. That's the only state that has a probability of occurring. And then the reward is -1. So I'll have probability of 1 of -1 plus gamma times the value of this state, which we already know is 0. Right? The value of this state is already 0, so we don't have to worry about it. So again, it's -1, right? It's like that. Right? This is basically what will happen. Okay. So even though it looks that, but this is how the computation happens, right? It's just one step reward. It is a -1, but there are 4 possible outcomes because there are 4 different actions. I have to consider all the possible outcomes, and basically end up getting a -1 again, right? Now, when you go to k equal to 2, what happens? Right? When k equal to 2, again you have to do the same thing, but now you can't ignore your V of S prime. You have to use the V of S prime also. Right? So what happens here, when I try to move up, right, I'll stay in the same state. So my V of S prime will be -1. Likewise, when I try to move here, I will move, but that state also has a -1. So that will be again -1. When I try to move down, I will move, it's a -1. Then I try to move west, what happens? I actually go to the terminal state, right? And that will going to have a reward of 0. So I'm going to get a -1 plus a -1, -1 plus a -1, -1 plus a -1, and a 0. Actually, it's not a 0, it's a -1 plus a 0. So that's a -1 as well, right? So I'm going to get 0.25 into -1 plus 0.75 into -2. Right, so rounding it off, you get 1.7. That's basically what has happened. So k equal to 2, it is like I take one step and then I take another step. Where do I end up with? So that's basically what we are asking here, right? So that's k equal to 2. Likewise, k equal to 3 is what happens with the three-step policy, and so on and so forth until you hit k equal to infinity, which is a final value function. So this is basically the v pi corresponding to the random policy. Okay, does that make sense? Right, and we can work on more complex problems, and you know, in one of the later videos, you will see a slightly more complex illustration of value iteration, policy iteration, and the different ways of solving this MDPs. Okay, so this particular computation that I demonstrated to you is essentially implementing these set of equations here, right? So where you have k on the right hand side and k plus 1 on the left hand side, right? This algorithm, right, this algorithm that you see on the screen is not quite that. It's slightly more complicated, because when I'm looking at the first state, right, I'll be using k. But what do? I update the v of s to Vk plus 1 of S, right. That is what I do here. So, when I come and look at the second state, but if I have to access S1 on the right hand side, I will actually be using Vk plus 1 of S1, because I have already updated the value when I looked at S. See, I start from S1, then I go to S2, then I go to S3, then I go to S4, right. So, S1, S2, S3 is how I am looping. So, when I first come to S1, I am going to compute Vk plus 1 of S1, right. When I go to S2, if I have to access V of S1, what I will have there is actually Vk plus 1 of S1, right. So, it is not like I take k to the right hand side and get k plus 1 on the left hand side. Depends on the order in which I am doing the computation, right. When I am actually looking at the last state, like say Sn, right, every other state except Sn will have Vk plus 1, Sn alone will still be using Vk. It's a slightly kind of a asynchronous computation is what is implemented in this algorithm, right. So, it makes sense, right. So, this algorithm is a little efficient way of implementing it, but it does it in an asynchronous manner, does not quite match the k plus 1 explanations that we have been giving, right. But rest assured that this implementation also will converge to V pi eventually, okay. So, that is basically it, just that makes it a little bit more efficient.